So good morning, everyone. Thank you for joining us for this last session on the last day of the Regulatory Information Conference. You're joining us for session TH23, More Than Mapping, Improved Earth Sensing Technology for Future Site Characterization. My name is Laurel Bauer. I am the Chief of the Structural, Geotechnical, and Seismic Engineering Branch in the NRC's Office of Nuclear Regulatory Research. So we've proposed today's session as a place to discuss what site characterization may involve 10 years or more into the future. Before I really get into the nuts and bolts of the session, I wanted to go through a few housekeeping items. So we will have a question and answer session at the end of this session, and you can enter your session using the QR code up at the top of the screen, and I believe that QR code will be available throughout the session. Other things to note is just please silence your cell phones for the duration of the session. Okay. So, as we've seen throughout the RIC, advanced nuclear technologies are expanding, and they're expanding at quite a rapid pace. And so this is really influencing in a huge way how and where nuclear power plants may be built. And the site characterization remains a critical early step in the process for looking at new sites. At the same time, there have been advances in earth science that can provide more data on the site with better quality over a larger area and in less time. It is these technologies that we hope to focus our discussions on today. Okay. So we'll begin the session with brief presentations of different geophysical methods used for site characterization, with each of our experts focusing on a particular area to provide context for what is the state of the art and what improvements could be considered before closing with a discussion session on what technologies could mean for future nuclear builds. So we have 4 experts on our panel today. Our first expert, John Diehl, is the president and co-founder of GeoVision, which has provided geophysical services, including site characterization, for over 30 years. John holds both a master's in civil engineering and an MBA degree from the UCLA. Our next speaker, Dale Rucker, is the Chief Technical Officer of Hydrogeophysics Incorporated, where he has worked for more than 20 years. Dale holds a PhD in hydrology and water resources, as well as an MS in civil engineering and a BS in mechanical engineering, all from the University of Arizona. Our next speaker, Tim Johnson, serves as the principal computational geophysicist at Pacific Northwest National Laboratory, which he joined in 2010. Tim holds a PhD in geophysics from Boise State University, in addition to a bachelor's degree in geophysics and a bachelor's in civil engineering from the same institution. And lastly, Jason DeJong is a professor of civil and environmental engineering and the director of the Center for Geotechnical Modeling at UC Davis. Jason holds a PhD and an MS in civil engineering from the Georgia Institute of Technology. So thank you for being here to our panel, and we're looking forward to hearing from each of you. Now, John Diehl will begin the presentations with a look at advances in seismic methods.
Good morning. Thank you, everyone, for coming. And I've been given a big topic, and I've only got 15 minutes, so bear with me. But I've already been introduced, but I wanted to show you this picture of this knucklehead standing under this precarious pile of rocks. But anyway, it's more about GeoVision. Since 1995. All 5 founders are still involved. And we started because we couldn't find anyone in Southern California who could do the kind of high quality geophysics that we needed for a particular project. But the most important thing is these are some of the projects we've done worldwide, because of the role of site characterization and particularly borehole and surface geophysics, GeoVision's had an opportunity to be involved in a lot of projects. And it's on the basis of these that we have some credentials in this business. How do seismic methods help geotechs? Well, it's site classification is a big one, determining depth of bedrock and water table, rippability of rock, soil and rock properties, fault location and orientation. I won't be talking much about that today, but mostly the shallow geophysics, and also data for site response analysis. Currently available seismic methods, I'm going to be talking about two categories, surface methods and borehole methods. And in the surface methods, seismic refraction, seismic reflection, and surface wave methods, including SASW, MESW, MELW, love wave, H over V spectral ratio, array microtremor, refraction microtremor. But what I want to point out here is that the first two, seismic refraction and seismic reflection, are very well known. They've been around for a long time. They have ASTM standards. But as far as surface wave methods, we don't have standards for these. So basically, we're using published literature, our own procedures to accomplish these methods. When you look at surface wave surveys, we've settled on what we think is the right approach. It's a multi-method approach, and the reason for this is that when you come to a nuclear site or any other site, you don't always know what you're going to find. But the advantage of this is that when, let me see if it's working. Yeah. So in the graphic on the left and on the right, you see a combination of a variety of surface wave methods, and they should all overlap. You should be able to get a consistent dispersion curve when you evaluate the data from all these methods. And then on the right, you can see we're overlaying also borehole geophysics, the suspension logging. So all these methods are complementary. And here is an example of the different sources that we can use. The small hammers are useful for shallow characterization, and the larger hammers, of course, for deep site characterization. For borehole methods, we can talk about, there are three main methods that are being used in site characterization at nuclear plants right now: downhole seismic, crosshole seismic, and P&S wave suspension logging, sometimes referred to as the OYO method. And once again, the first two are very well defined and understood and well used, and that we have ASTM standards for them. Suspension logging, even though it's been around for 35 years, there still isn't a standard that everyone follows. I mean, we've had an established procedure that we've used for 25, 30 years, but it's not something that's published or very well dispersed. If you look at the borehole techniques for shear waves, you look at, here's an example from, I think this is from Abu Dhabi, a nuclear plant there. Suspension logging uses a single tool that contains the source and the receivers. Crosshole or downhole uses receivers that are lowered down the borehole and with the source at the surface. And crosshole is the source in one borehole and the receivers in another. And what you see here is the difference in resolution. So the lowest resolution is downhole method, which has been around for probably 60 or 70 years. And then crosshole does a much better job but both of those have a known resolution of around 5 feet, 5-foot spacing, whereas suspension logging is much higher resolution, usually 3 times that resolution. And you can characterize much smaller features with that tool than you can with the others. So, what's the future for seismic methods? Well, I think first of all, we need to bring state-of-the-art to state of practice, particularly for surface wave methods and for suspension logging. It just needs to be that, and when one of the things that suspension logging does for you is it has the characteristic of self-validation. And the reason for that is you have 2 receivers and a source. You can actually measure not only the receiver-to-receiver velocity, but also the source to first receiver, source to far receiver. So you can actually get a self-validation. You can check whether or not you're getting the right answers or the right measurement by looking at, because if you have the measurement where you measure the receiver-to-receiver velocity, at the same time you can measure 5 feet below that the source to first receiver velocity. So it's excellent, but not everybody's doing it that way. Well, so let's focus on surface methods. What's the future of surface methods? The first of all, we would like to see incorporating H/V spectral ratio into site response studies. And to illustrate that, here's a slide where you do a surface wave measurement and you get dispersion curves, maybe from multiple different MASW and passive arrays. You put that together and you come up with all of those light blue models are equivalent. I mean, they can give you the same dispersion curve. Well, which one's the right one? Well, if you didn't have anything else to look at, you would pick the solid blue, dark blue line. You'd say, well, that looks like that has the least error. But if you combine that with H/V spectral ratio in the lower chart, you can see that the dark blue line doesn't line up with what the H/V is measuring as far as the peak response. And then you can adjust your model to get to the place where the model matches the data. And so that would direct you to the dark red model in the top right graph. Back to the future. The second item is explore using 3-component sensors for better joint Love and Rayleigh wave analysis. So this is something that I don't know of anybody I think it's being done in research, but it's not something that's being done commonly. The third item there is exploring how artificial intelligence can help with better inversions and better modeling. And then finally, we need to standardize methods on measuring damping. Right now, there's a variety of ways to do that. Well, let's now look at what's the future for borehole seismic methods. Well, first of all, in our opinion, we need to confront the issue of anisotropy. And it does exist and more often than you think, but we don't usually check for it. And I'm going to be showing you an example in the next slide. But how should we check? Well, one way would be, if you're doing downhole measurements, to do multi-plank orientations. And the second way would be develop new suspension logging tools that also have built-in orientation. Because right now, the suspension tool, as it lowers through the borehole, it's allowed to spin freely in the fluid. Well, that means at any one moment, you could be measuring different velocities. And we saw this particularly in our work up at INL, in the different basalt layers, where if you were oriented, you could get different answers. Most of the time, in most materials, you get exactly the same answer logging down as you do coming up. But suppose the tool rotates a little bit and you have a lot of fracturing, you can get slightly different velocities at a particular depth. So here's an example of multiple plank operations that characterize shear wave splitting. So what you see here are two different downhole measurements at the same borehole, and you can see this is going down to, I think, 500 feet. But what you see is if you change the orientation of the plank, you can get different shear wave velocities at the bottom of the hole, and that's like a 25 millisecond difference in the first arrival. That's huge. Well, how do you know if you have it? Well, you won't know if you don't check for it. And unfortunately, in current procedures and standards, nobody checks for this. Another thing that happens that we've seen is, even though you align the plank and you align the borehole, the downhole sensor orientation with the plank, so you think, okay, now we've got everything polarized. We're hitting the plank and directly in the axis of the orientation of the tool. That's not true. And here's an example. So on the left side, you see downhole measurements with the tool oriented with the plank. Well, the problem is the orientation of the materials in the formation don't stay with the plank. They've rotated. So what you see here is about a 50 degree rotation. If we rotate the data 50 degrees, we get a much cleaner measurement. But it's interesting that most of the time, and even in the ASTM standard, you don't check for this. So what's the future for borehole seismic methods? Well, one thing also becoming more and more of a topic is over-consolidation ratio. Well, you can use Crosshole to measure this, both SH and SV. And currently, the Crosshole method, as it's commonly executed, only measures SV. So it's something to think about. If it's something that's needed in design, then we need to start measuring both SV and SH. And we can do that right now with two different methods, but if there were Crosshole sources that would produce both SV and SH, that would be better. By the way, we built one of those. and we wore it out at Savannah River doing 10,000 shots, so it was interesting. All right, lastly, looking at the future, there's a possibility of using borehole gravimetry to perform in situ size density measurements, basically doing vertical microgravity. But that's something I don't think is being done very much. And that's it. I think we'll have questions later, right?
Yes. Thank you, John. So we will hold applause until all of our speakers have had an opportunity to provide their presentations. And we'll also answer questions at the end. So next up is Dale Rucker, and Dale will present on airborne electromagnetic methods.
Well, thank you for the opportunity to speak with you today. I'm going to talk about one of my favorite subjects of all time, geophysics. You'll get a lot of those talks today. A little bit about me. I do have a hydrogeology degree from University of Arizona, but in that degree, I use geophysics to solve hydrogeologically based problems. Basically, where does water go? And electrical and electromagnetic techniques tend to focus well on understanding hydrogeology. What I'll be specifically talking about today is electromagnetics collected from a helicopter platform. And you can see in the picture that I have up, you have a helicopter, and hanging below the helicopter are a couple of large loops, and those loops swathe back and forth across the landscape, making measurements of the electrical structure of the ground. And then from the electrical structure, we can understand hydrogeological or geological concepts that would help in, say, nuclear reactor siting, or would help in some sort of construction, or understand contaminant plume movement. So a little bit about my philosophy of geophysics. Basically, there are only a few ways to interrogate the Earth. You could either have surface geological mapping, drilling, or geophysics. And in the first one, surface geological mapping, you're going to have to infer what's happening below ground by seeing what's happening above ground. In the second case of drilling, you get very detailed information, but you get it at one spot. And you can go depths of thousands of feet if you'd like. In the third, in geophysics, you get lots of information over a very broad landscape that can be collected inexpensively, non-invasively, and in some cases, we can do repeat measurements to look at changes over time. And what I'll be, again, speaking about specifically today is the airborne method. You can see on the right-hand plot that I have different modes of geophysical data acquisition, from borehole techniques, which John touched on a little bit, surface methods, data collected from a drone, the airborne platform with a helicopter or a fixed wing. I show it a little bit larger here because that's what I'll be talking about. And then you can collect data from satellites as well. We have satellites going around the Earth collecting gravitational data. We have satellites going around Mars. So that's another platform we can collect data. With the airborne geophysics specifically, we can deploy a variety of different tools without terrain or vegetation issues because we're above all that. We can cover up to 200 miles per day, depending on weather and how far the helicopter is from its base of operations. And then we can also investigate up to depths of 1,000 feet or more. So sensors that we can deploy on an airborne platform include magnetometers, which measure iron-based items in the ground, gravimeters, electromagnetic sensors, and I have it boxed because that's one I'll be talking about today, radiometrics, LIDAR, hyperspectral and multispectral imaging, or infrared and thermal sensors. The first three in that list allows us to see pretty deep into the Earth because, for example, you got large intrusive bodies that can be covered up with 1,000 feet of sediment. We can still see it with magnetometers. Two of the techniques have an active source, and that would be electromagnetics and LIDAR. The rest of them just passively measure whatever the Earth gives us. And then the last ones, radiometric, LIDAR, hyperspectral, and infrared, sees very superficial images, very superficial information. That's because they're very high frequency, and so the information just doesn't penetrate very far. So key considerations when conducting an airborne measurement is the weight and size of what the instrumentation that you're carrying, the power consumptions, vibration, stability, and then how you're actually going to collect that data. Where is your data collection system? On the right-hand side, I'm showing again the helicopter with the loop hovering above the ground about 100 feet. Between the helicopter and the loop is a gasoline-powered motor generator. And so for our electromagnetics, that's how we power our system. So if you're not familiar with electromagnetics, you can harken back to your Physics 2 days, the right-hand rule. You got an alternating electrical current, which creates an electric field and a magnetic field. And so that large loop that you see below the helicopter is our transmitting loop. And we got an electrical current going in that loop, again, generated by that motor generator. And then that sends off basically magnetic field into the ground. And that magnetic field encompasses or it interacts with electrically conductive bodies in the subsurface. And through induction, new currents, electrical currents called eddy currents, will be generated in those electrical bodies, and then they will send up their own magnetic field, a secondary magnetic field. And we have a smaller loop in the center, in this case, in the center of the transmitting loop, that will measure the voltage received by that magnetic field that's coming back from the Earth. So the data, as we collect it across the landscape, will get a series of one-dimensional soundings. And then from these soundings, we'll do some modeling, inversion, and stitch together 2D and 3D representations of what the Earth looks like from an electrical standpoint. Now, why do we care about electrical properties of the subsurface? Well, here is a chart showing electrical conductivity and resistivity values, they're reciprocals of one another, of common Earth materials. First thing you'll notice is that the values range over several orders of magnitude, from very low values of conductivity to very high values of conductivity. From there, we can start to see how different Earth materials range in resistivity values or conductivity values. For example, we have very competent hard rocks with very little pore space or no pore space at all on the high end of resistivity, low end of conductivity. And then as we move across the values, we see that once you start getting more into the moisture, increasing in moisture content, the conductivity increases. Or the additional of certain minerals, such as clays, the conductivity will increase. The ionic strength of the pore water, for example, seawater or some very contaminated waters with high inorganics will also have high conductivity values. And then also some of the more competent rocks will have sulfides or graphites that will make the rocks electrically conductive. So that's first. So you're looking horizontal from left to right. Another aspect of this data is that if you look up and down, a range of resistivity values can have different possibilities of what their meaning could be. For example, between 1,000 and 10,000 ohm meters on the resistivity scale, you can have various types of sands and gravels, or maybe a saprolite that's slightly dry, but because there are multiple possibilities to a single resistivity value, this lends a little bit of ambiguity to the methodology of measuring conductivity of the subsurface. And so that makes it a little bit fun. You have to use a little bit of hydrogeological or geological intuition to understand exactly what may be happening. So let's get into some data. I would love to show you some of the data that we've collected, but I'm under NDAs and contractual agreements not to show the work that we do, but I was able to grab some very good examples from the scientific literature, and this one's from Wu et al., in which a series of lines were collected in Southern California. So the upper plot just shows a map of the area with some lines that the helicopter traversed back and forth, back and forth. And then at the bottom, we see the actual data. Now, I had a client one time refer to the data that we show as tie-dye geophysics. Most of these data are going to be in some sort of rainbow color scale. And with in most cases too, the reds will be electrically resistive, and then the blues will be electrically conductive. And so as we move across the landscape, we can see on the left-hand side, it looks reddish. It's resistive, and that's over the granite mountains. So competent mountains are resistive. And as you move to the right, we get into the basin. The pediment fault has been infilled by some evaporite, so it gets a little bit conductive. As we move towards the center, we get into where that Playa Lake is located, the Leech Lake. It's very electrically conductive in the blues there, and then we move on across the landscape. So there's several features to this data. One, you can see how much data that was collected. This is a 10-mile section, and to collect 10 miles would take maybe a couple of hours at most. So it collects data very rapidly. The second aspect is how deep we're seeing, upwards to 1,000 feet, strictly from a helicopter hovering above the ground. Another aspect is we can start to identify structure in this data. For example, as we move on the left-hand side from the granite mountains to the pediment fault, where we know in Western geology, we typically have a basin and range system. And we can identify a fault by the abrupt change in colors from blue to red. So that lines up with some superficial mapping that has already been done. And then as we move across, we can start to identify potentially areas with sands and gravels, which would be more resistive from the last chart that I showed you, versus some clay type of materials that would be closer to the center where we have that playa, and we know that playas will collect fine-grained sediments and settle out. And so that's typically what we see there at the Leech Lake. In another set of data, I'm showing it now as a series of ribbons or fence plots. Again, this is data collected in California. And what we're showing here as we move from the east side, which is the right side, towards the west, we're moving from a mountainous area into a basin. And this data are being used to help calibrate groundwater models to better manage the aquifer and the water usage for whether it's municipalities, agriculture, or what have you. But on the right-hand side, we see where the materials are resistive because the basement bedrock. You go left from there, it gets a little bit more conductive. We're getting some infill sediments again. And then as we get into the basin, we're starting to see some very detailed layering of fine-grained sediments, which would act as the aquiclude. And then sandwiched between them will be some sands and gravel layers, which are the aquifers. So this would give, one, the groundwater modelers an idea of the geometry that they need to incorporate at a much finer scale than they had with, say, the boreholes alone. And then it would also give them the opportunity to target where, how deep that they would need to drill in extracting extra water that they would need. Another way to present data is just a 3D block model. Because we swath back and forth, we can stitch all this data together, model it all together as a continuous three-dimensional body. And again, this is another example of finding fine-grained sediments such as clays and how they would be structured within this basin relative to the sands and gravels that would be needed for groundwater extraction. In the center, where it's pinks and reds, those would be the mountains on the east side. And again, those are more resistive materials as we'd expect mountains to be. My last data set that I'm going to show is mapping faults in the Mississippi Valley. This is a USGS project. And you can see on the far right-hand side a map there of the area of focus, and there was a series of lines traversed back and forth over a very broad area of the Mississippi Valley to map the geology And in this one, what I wanted to show that may be appropriate for siting nuclear reactors is the identification of some very important faults. So near the middle, we see a transition going from very resistive to conductive, and we see a series of faults that are identified in this geophysical data. So from my perspective, it would be important then to be able to understand where those faults are located, even if we have 100 feet of material on top of it that may be hidden from normal mapping exercises, whether it's from drilling or from surface geological mapping. Those may not be readily apparent. And so what the airborne data or any other geophysical data would be able to do is help identify structure, and that's important for nuclear reactor siting. So going back to the idea of reactor siting, here's the Clinch River site. I believe it's being considered for a potential reactor. The area there on the right-hand side is shown. It's about 2.2 miles across at the largest spacing. So if we were to design an airborne survey over this specific area, it may look a little something like this. We would traverse back and forth at a very tight spacing in one direction, and then we would follow it up perpendicularly with a much broader spacing, and those are called tie lines. So it allows us to bridge from one line to the next. So benefits of conducting an AEM survey would be that you get complete coverage of an investigation area. You get a 3D block model showing the electrical structure, and we've already shown that electrical structure can be related to geological or hydrogeological information. We can get stratigraphy, we can get faults, fractures, we can understand karst. In the southeast particularly, where you have large limestone bodies, karst could be a problem. We can combine the geophysics with other types of data to fill in data gaps. For example, if you've already have drill hole information, maybe the geophysical data would fill in between the boreholes to allow the bridging of information that way. We can help eliminate undesirable areas very quickly, for example, identifying those faults. And then lastly, once we collect this data, it can be used for lots of different other projects. Maybe state level, they're looking at highways, or groundwater models. The data can be shared with other agencies to help reduce the costs on everybody's side. Some final thoughts. When we're doing a geophysical survey, we can think about budget, the scale of the survey. If it's a small scale, it may not even be appropriate for airborne electromagnetics. We could use another technique to collect electrical information. The resolution and target size, timing. It's sometimes difficult to get a helicopter out when you exactly want it, and the types of deliverables that you need. And advancement continues. So John has already mentioned the machine learning aspect. Machine learning is being applied to airborne electromagnetics to help speed up the modeling process. And then statistical procedures for correlating conductivity to, say, lithology or stratigraphy. So that's all I have for my talk. Thank you.
Great, thank you, Dale. Our next speaker is Tim Johnson, and Tim will be discussing site monitoring with electrical resistivity measurements.
So thank you all for being here. I realize it's the last session, the last day of conference, and I've been there, so appreciate you being here and appreciate the chance to speak to you today. So I'm going to be talking about a method called electrical resistivity tomography, and it's similar in what it does to the method that Dale just spoke about, in that it measures the electrical conductivity of the subsurface, but it uses a different physics. So I always, when I talk about it, I like to go to this medical imaging analogy because people are kind of familiar with that. So we have a subject here, and this subject has basically electrodes attached to him, and those electrodes are used in this measurement, ERT measurement, to inject current through 2 electrodes. So you can imagine it's a very small amount of current in this case. And when you inject current into the ground, that sets up a voltage in the ground or potential that you measure across many other electrodes. You take many measurements like that, put it in a data processing algorithm called inversion, or this is where the tomography comes in, and an image comes out. So in this case, we have a 2D image. You can see the outlines of the lungs there, and you can see the heart, and you can very faintly see the spine in that image. But you'll notice that it's, in comparison to medical imaging you might be familiar with from an MRI or something, it's really blurry. And that's something we always deal with in geophysics, is that we're limited in our resolution, so that the images that we're interpreting, you have to interpret with your geophysics goggles on and realize that these are blurred versions of what's actually there. But the trade-off is that the instrumentation is really simple. We couldn't do an MRI of the subsurface, but we can put electrodes on the subsurface to image it in the same way. So, and that's what we're showing here. So here we have surface electrodes. These, if you can see the little orange dots in this case, every one of those is an electrode. An electrode is basically a piece of metal, about this long, pushed into the ground, and it's collected to cables and some instrumentation. There's 3 there. You do the same type of processing, and out comes the image. In this case, this is an image of the electrical conductivity of the ground. You see that this is, sorry for the confusion, this is flipped just from what Dale was showing, because I'm showing conductivity, he was showing resistivity. So here the blue lines are low conductivity. So you can see some layering there. And this has to be interpreted somehow, and I can't emphasize enough that geophysics should never be interpreted in a vacuum without other information. And so you always have to have other information to try to interpret what these images mean. And this is one of the reasons we put Jason last, is because he's really good at integrating information like this. So, and he'll talk about that. So in terms of the instrumentation, so I showed you some surface electrodes there. You can also do cross-hole imaging. I'll show you some examples of that. You have to have non-conductive casing in a borehole. You can strap electrodes to the outside of the casing so they're in the annulus, and then you can use the borehole for other things. So there's some examples, some stainless steel electrodes on casing there. That's what the instrumentation looks like down in the right-hand corner. This is a big monitoring array, so you wouldn't necessarily use this much instrumentation for doing just like a static characterization image. And I'll show you examples of both of those things, but this instrumentation is available off the shelf. So I'll hurry through this because Dale talked about it a little bit, but electrical conductivity, this is what it's sensitive to and why it's useful. It's governed by porosity. It's governed by moisture content. My eyes aren't good enough to see my own slides there, so I have to read them. Surface area, groundwater composition or fluid conductivity, and temperature. So when like the image I showed you before, it could be, the changes in that image spatially could be governed by any one of these things, and this is why we need other information to interpret those images. But they do provide nice mapping in between. When we do time-lapse imaging, which I'll show you some examples of also, usually only one of these properties is changing in time, so you know as the changes happen in time what the change is, and that's one nice advantage of ERT that's really good for time-lapse monitoring. So here's one example of surface imaging. This is at the Savannah River site. In this case, this was actually an array that was installed to monitor surface infiltration through the clay cap. So this was this is where they disposed of contaminated liquids. When they were done with the pond, they filled it in and put a landfill cap, a clay cap over the top. And we installed an ERT array over the top to monitor for infiltration, surface water infiltration, precipitation through the cap. All I'm showing here is the first image. This is what we'd call the baseline, or a characterization image that's showing the change in conductivity within the pond beneath the cap. So these are all materials that they placed in there. But it gives you an example of the type of resolution that you might get at this scale using surface ERT. Again, our objective here was not to characterize, but to monitor. And so we didn't do any drilling, nor could we, because we would have had to drill through the cap. But just to give you an idea of what the types of resolution you might be able to see from the surface at the scale that you might be interested in for siting a nuclear power plant, for example. This goes down tens of meters or something. Just in a different geology here, this is also this is a cross hole image. This is at a site in New Mexico in a very dense, very solid, non-fractured rhyolite, so very low conductivity, high resistivity. This show you the type of resolution that you can get in a borehole. Usually we do cross hole when we can't get the resolution we need from the surface. As you get farther away from the electrodes, your resolution goes down. And so in this case, we needed very high resolution, and so we drilled a lot of boreholes. The little red dots there are where the electrodes are, and the blue areas are where we had gas sampling intervals. So you can see the layered geology there. If you can turn this around, you can see how it, how it varies in space. So just an example of cross-hole imaging there. So I'm now going to show a few examples of time-lapse imaging, which is what I work on mostly, and where I think the real advantages of ERT are. So in this case, we were. I might have to. Erica, if you could just stop the animation for 1 second. Thank you. So this, because I don't want it to be done before I talk about it here. So up on the top, this is the Hanford 300 area. The 300 area is where they made the the uranium rods for the plutonium reactors farther up the Columbia River. So they had waste ponds there. There's contamination there, right next to the Columbia River. So in this case, we were trying to understand how, when the river goes up and down the stage levels, it's a very dynamic river. How the river water intrusion into the contaminated area, how those patterns worked, because that governs how uranium contamination is transported to the river. So we installed a 3D array of surface electrodes there, and then we monitored the changes in conductivity as the stage river went up and down. And the reason this works is because the river water conductivity is about half of the groundwater conductivity. So the river actually acts as a tracer, the river water, as it's moving in and out. Okay, Erica, you can go ahead and start that again. So what we're showing here, the little plot up in the right-hand side is showing the river stage, and the red dot is showing where the river stage is. The blue isosurfaces there, this is actually a 3D image shown as isosurfaces. Those are the changes in conductivity. So darker blue is a decrease, a bigger decrease in conductivity. Lighter blue is a lesser. And so if I could point to it, we have a pointer. If you could stop it right there, Erica. Yeah, that's a good place to stop. But you see the darker blue areas, those are actually paleo channels that were guiding river water in and out. They were the primary flow pathways. That's okay. I think I could talk about it. Bottom. You got to really aim. So right in here, there's paleo channels there that were guiding river water in and out. So this, it was through this process that we identified those paleo channels. We weren't able to see them in the raw baseline images. We only were able to see them when we watched the river water coming in and out. So this is a process that could be, for example, important in a nuclear power plant that's situated next to a river body where there's lots of tidal variations or stage variations, and there's river water, groundwater interactions that need to be considered. Okay, this is my final one, and I'm showing this one mostly because it's so relevant to this industry. This is a project that we had with EPRI, and where we were demonstrating ERT monitoring for monitoring leaks from buried pipes. So this was at a cooling water pumping plant on the eastern coast, and we ran this project to demonstrate and to validate and to test how well ERT monitoring would work as a leak detection technique. So the bottom left image there, Eric, if you just want to click on that, That'll just rotate around. So this is the baseline image. I guess I didn't mention this before, but the baseline image is a characterization image or a static image that you collect before the changes you want to see. And then as you do time-lapse imaging, you subtract that baseline image out so that you only see what's changing over time. And so that's what it looked like. You can see the pipes there coming from each one of the pumps. There were 4 pumps in this case, pumping water out into the ocean, cooling water. So that's what the conductivity looked like. The blue stuff is sands on top, and then as you get lower, you're getting closer to the groundwater, which was saline, and so it's getting more conductive. So we did a test. If you look, we caused a leak. So we put a pipe in the ground and we ran water into it, and then we imaged it over time with the ERT system. And that's what's shown on their top. You can see us putting water in the leak pipe with the hose that's right over the top of one of the discharge pipes. So if you want to just click on the lower right image, Erica. So this is showing the change in conductivity over time. That's basically outlining where the leak water goes as we're dumping it into the pipe. These are images that occur every 10 minutes that we were doing. And if I didn't mention, all of this is autonomous. You can set it up to happen autonomously and in real time. So when we're monitoring things like this for cleanup contractors, for example, it'll take the images, it'll send the data to PNNL, do the processing, and then send the images to a website so that they can see what's happening underground as it's going on. So that was my last slide. Just some examples of ERT monitoring there. And I guess we'll wait for questions until Jason's done. So.
Wonderful. Thank you, Tim. So our final speaker is Jason DeJong, and he will touch on in situ methods as well as how site data is integrated into a coherent model of the subsurface.
Good afternoon. Thanks for staying with us till the very end. Last session, last talk before some questions. Just want to give a bit of a background. My expertise is originally and continues to be in development of in situ, different testing techniques, but also in a variety of other roles as a technical reviewer for some large site characterization projects with budgets of about $2 million, and also studying historic legal claims with respect to the private industry for geotech, and also then as an educator teaching site characterization. I wanted to touch on and look at this question that's been posed in a slightly larger perspective. And so also want to mention that we're a bit pressed on time, and so we're going to go through some of these slides a little bit quickly, but the full set of slides is available for everyone for download. And so if you want to go back and look at some details, feel free to. One of the opportunities that we've had is to work with an insurance company to review geotechnical practice over a span of about 25 years. One of the interesting observations that came out of reviewing about 1,600 claims levied towards different private consultants was that about 50% of those were attributed to mischaracterization of the site and the site conditions. And so a brief image for that, if you look on the left-hand side, the left vertical axis is frequency of occurrence, the right is percent payout per claim. And you can see that the two primary ones are with respect to characterization of the site. And so that's really the big issue and the big challenge in geotechnical practice as a whole. Those few design mistakes that we make, they're not very often, but they are expensive. And if we looked through all those different case histories, there's 3 observations that came up. One was that oftentimes we have insufficient documentation and characterization at the time of the work that the work was performed at, and that is a very particular legal foundation or basis. Lack of internal or external peer review, and a lack of a systematic approach to the site characterization. So we've made some efforts to go in that direction, to provide structures for people to follow. This is one of those structures, and we're talking about site characterization as a whole, not site investigation as a particular task. But in site characterization, we're really beginning on the left-hand side with a phase of inductive reasoning where we're really conceptually imagining the site, both the functional mechanisms of performance and integrating that with the geologic model. We're doing, in the second phase of scenario assessment, potential preliminary analysis. It can be relatively simple and straightforward, but it allows us to identify what's critically important. Then in the bottom left-hand side, the site investigation, which includes the different tools that have been spoken about by my colleagues. And then moving into site idealization on the upper right-hand side. And I think it's very important to separate the data we collect from how we interpret and simplify that data for subsequent analysis. And then we go through design. So it's not a linear process as we wish, but there are some iterations inside of that, and that's what I'm trying to capture right there. And there's 4 components here that I just want to comment on briefly. And again, I'll leave you in the future to take a look at some of the slides in a bit more detail. The first one, though, in the top left, is realizing that in many cases, it's the geologic features that really dictate system performance as a whole. And so it becomes really important for us to be able to understand and interpret in between the in situ data that we generate, which is obviously of far less than 1% of the volume of soil engaged in the performance mechanism. So as a simple example, this is a vertical cut from LA. If we went in with 2 boreholes and about 2/3 of the way through, you might think those layers are connected. But in the alluvial environment, the depositional environment, the spatial variability is much more variable than we ever wish or hoped it would be. And that's a persistent reality that we always need to check ourselves back against. There's other examples where we can think of the geologic formational processes in a relatively broad, flat valley. We might have a meandering river which might avulse from time to time, and we can get these small pockets which may be potentially liquefiable. And an example of that is shown, and this is from the Eastern Sierras, where there's this dam alignment, and there's a linear array of about 30 different CPTs in that case. And we can take a look at those CPTs in cross-section, and the geologist team can go through and identify the various different geologic units. And we have a hard time distinguishing, just looking at it from this scenario, how the ground will perform. It really depends also on the geotechnical properties that will dictate, in this case, the susceptibility to liquefaction resistance. So we're going to come back to this figure a little bit later on again. In the in situ site characterization realm, again, there's 2 things that we really want to think about. And if we a priori have already hypothesized about the geologic conditions and the performance mechanisms, this whole process of site investigation becomes one of verification instead of one of discovery. We're testing what we believe will be there and what will be encountered. And that, in order to do that well, it obviously requires us to use state-of-the-art technologies, but also that we have hypothesized the failure mechanisms and the geologic model. And so, for example, if we, in this stratified material, built a small infrastructure, we might have a relatively small failure mechanism, which could be in a localized weak pocket. Whereas if we construct some larger mechanism or a larger facility, then it could be cross-cutting through multiple different layers. And as a result, it would be more appropriate to use a mean or a median type of value instead of maybe just a minus half sigma representation of the engineering property. As we try to understand spatial variability, we have 2 competing interests. We need to obviously have site coverage, and this is a very simple, idealized layout. And we often are thinking about this as an engineer, but it also becomes really important to embed at non-equal spacings, arrays and clusters, which will enable us to look at spatial variability and the uncertainty that exists. Paired with that is an approach of testing in clusters. We're using multiple tools densely spaced together because we need to be able to differentiate what is the variability due to the natural depositional processes, geologic depositional processes, compared to differences in how the tools function. And so both of those are recommendations which are often overlooked on various projects. And so again, those allow us to cross-verify properties, understand sources of uncertainty between the subsurface and the tools, and give us the intensity of data that we need in order to move towards statistical analysis and probability of failure-based design. So at the end, we have an outcome, which is site-specific database of conditions and parameters expected to control system performance and design. There's a whole host of tools. I could talk for an hour on each one of these. We're not going to, obviously, but the geophysics has been covered well by my colleagues, but there's a variety of other probes that continue to be developed and adapted. And in using any of these, they depend on the geology, stratigraphy, depth, the properties needed, and the analysis and the design. And again, we're always looking to be pairing this with the geophysics, with the in situ testing, but also with samples, which are our ultimate ground truth through laboratory testing. And we're not talking about that one so much right now. Moving forward in 10 years, what do I expect? If you look at most of the ASTM standards, the goals of most of the standards are to lock in functional actions, to lock in penetration at a certain rate, rotation at a certain rate, loading at a certain rate. I think we're going to go away from that. I think we're going to move instead towards trying to control how the soil responds to the test. So we want to ensure we have a drained response or an undrained response. So we're going to be adapting in that realm. Another one is going to come through technology. The ability of miniaturization of sensors is really incredible. It's coming from the other fields and being driven by other industries, but we can benefit from that. And so there are probes now that you can assemble that might have nuclear magnetic resonance, as well as hyperspectral, as well as optical probes, all in a single device together. Another one is measurement while drilling. The concept of this is you basically instrument the heck out of your system and you capture as much information as you can, and we're going to be really depending on ML/AI to provide information about that. The first international conference on this topic is being held in the Netherlands in September, and so it's emerging. Here's an example output. For example, where you're capturing all kinds of rig action, all these, what used to be qualitative information about your site activities are now becoming quantitative and documentable and useful. And then we're going to see increased autonomy of the vehicles. We see now in the tailings industry that the various vehicles and testing processes can be done completely remote for the safety of personnel. And then if I take a look and I think through what are the challenges, one of the challenges we have is our old technologies. We like them because they're familiar, they're simple, they're inexpensive, and they're known. But they are also of poor data quality by today's standards. They are usually spatially separated. They can be highly operator dependable, etc. And so those, while they got us to this point, are now the anchor that's arguably holding us back. The second part, which I've seen, and arguably this is more in the realm that I have worked in a little bit more, which is looking at various regulatory agencies and owners at the regional, state, and federal level with respect to embankment dams. But we see challenges with respect to different agencies being insular, how the contracts basically demotivate innovation, how the documents between different agencies, even if they might co-own a facility, differ, and there's not a unification there. And so I don't know your industry as well, but I've seen these be hindrances towards innovation at other points in time. Let me make a few comments as we move forward towards idealization. And just for the sake of time, I'll bounce over a couple slides. But what I want to separate and emphasize here is that there's a difference between the characterization of the site versus the prior step, which is the investigation of the site. The investigation of the site gives you the data report. It gives you the factual data. But then the next step of interpreting and invariably having to both reconcile and then simplify the realities that geophysics, in situ tools, and laboratory tools give us, that is a process of discernment that we do, hopefully, with a large group of folks with different expertise. But how we go through that and how we document that is really, really important. We're looking to get representative baseline values as well as other variances of those. We want to hypothesize the potential unknowns and their consequences. We want to divide into the subzones of how we're going to model and how we're going to analyze this. And we want it to be a process which is easily reviewed and documented for a continuous review into the future. So we end up with a well-documented representative site conditions that communicates the processes and decisions that were made for simplification, parameter selection, as well as tracking all the different uncertainties that we have. Again, I'll go back to the same scenario. This is that site on the eastern US, and this is just the layout of the different CPTs across this about 2,900 foot long embankment. You can go through and do geostatistical modeling and develop correlation structures, and from that do scenario realizations. And going through that process, and I'm going to skip the next 2 slides, which contains the information on that, you can end up with, through a series of simulations, identifying which locations, in this case, are more or less susceptible to liquefaction. And you can see 2 observations here on the upper right-hand side. That's where the stream has continuously meandered and reworked. And so this is a pocket of shallow but liquefiable material that can be treated through ground improvement. On the lower left-hand side, there's that long horizontal lens, which was attributed to being a sheet flow off the Eastern Sierras. In that case, that's really out of the depth of standard ground improvement, and they're having to go to some other mitigation measures in that case. But what's neat is that if we take these geostatistical analysis and we incorporate it with the geology, we can now have a robust correlation, if you will, or confirmation between the expected engineering performance through a series of numerous simulations based on geostatistics, and that being ground truth and what the geologists have interpreted at the same time. And so this provides then a way in which we can track systematically and in a reviewable way the baseline scenario as well as also some pretty different, extreme scenarios of both loading but also different potential site characterization conditions or in situ site conditions. Last thing I want to comment on is the visualization tools. We have been driven, thankfully, by video games and other things to be able to imagine through a pair of lenses what we never thought possible. And I have to point out BGC engineers, and I have no affiliation with them, I have some folks I collaborate with there. They have really piloted this. And you're looking at 3 photos that they shared with me where they are in an immersive environment where they can walk through with a HoloLens or the Apple Vision Pro an integrated vision of the design of the facility as well as laboratory data, in situ data, geophysics, and all the rest. And you can do this with people in different offices around the world, and you could also do it with someone wearing the headset actually in the field. So if someone is seeing something in the field, they can put on their lens, the principal engineer back at the office can put on their lens, and they can see the same thing, and they can have a conversation about it. And so this is going to become part of the future as well, without a doubt. And so with that, just a series of comments to kind of wrap up, and I'll just briefly summarize these. The characterization is a process. Site investigation is a task. Site characterization is a process. Begins with the geologic model and expected failure mechanism and goes all the way through construction. We have to understand the geologic site formation processes and the anthropogenic history for us to fill in all of the gaps between the sparse data sets that we collect. No matter what the budget, it's still going to be sparse and still not going to be enough. The advancements in site characterization are going to come from automation, different computational tools. It's going to be driven by safety as well. And in terms of upskilling, there's a key part of upskilling, if you will, and also updating of regulations to really what's now state of the practice in industry or state of the art as well. And I think there's a lot of opportunity there, and there needs to be an environment where those advances can be incorporated in an efficient manner. And then this step of site idealization of how we simplify the complex reality of the Earth in a way that's traceable and documentable is going to be really key as we move forward. And the last part then is really we're trying to get down to risk and to manage and to mitigate risk. And if we do that, we have to have all these different pieces together, which will enable us to know those uncertainties better, to better do probabilistic design. So that's the last slide I have. And so with that, I think it's time for questions.
Thank you, Jason. So I'd just like to take a moment and recognize all of our speakers on the panel today. So thank you all. And as our coordinators are queuing up questions, I wanted to get to one of the questions that we had when we convened the session. And Jason, you touched on this a little bit, and I think you've all touched a little bit on the state of practice, but it's the distance between the state of the art and the state of practice in site characterization, and particularly for nuclear sites. We've heard about a range of technologies and how they're advancing. And I'd like to give each of you an opportunity to take a few minutes and describe how you see that distance. Is the state of practice lagging the state of the art? And is the gap growing or shrinking? And I will start with John.
Thank you. Yeah, I think it'll be kind of vulnerable here because, you know, within a company like GeoVision, there's a particular characteristic of our, you know, for example, suspension logging, where we've been able to create better ways of implementing that tool, and we hold that as a corporate value. And it's not something we've, in the past, we really haven't been interested in doing participating in an ASTM, developing an ASTM standard. But I think that doesn't necessarily help the community, and if we're competing in an environment where other people want to be able to do the same things we do, we need to help in that regard. I don't know if that helps, but.
Well, I too work for a small company where we're a geophysical service provider. If you look in the literature of what's being done with the geophysical data between high-level geostatistics that Jason presented or machine learning that was touched upon today, as a small provider, we don't have those tools quite yet. So we're relying a lot on manual interpretation or interpretation with, in the framework of boreholes or other information that already exists. And if we can move to something that's a little bit more robust and quick for those interpretations, that would be likely more accurate. I think that would help the industry as a whole.
So I'm trying to think of how to answer this one. So I work for a national lab, and most of our work is for the Department of Energy, and so we don't, I guess our end of this is getting things to the end of the row, and then the national labs really love it when we, when things are commercialized and pushed out. And so I see some of the challenges we deal with in dealing with that in terms of, for example, adoption of the methods that we use by site contractors who are doing cleanup at Hanford, for example. There is a hesitance just from a regulatory perspective because the new methods are so uncertain to them. Not uncertain, but unfamiliar to regulators. If there were a path to help regulators become more comfortable with new methods and research that's coming out, I think that would help. That would help some of these methods, be more adoptable in industry. That would be my comment.
So part of the question was, what's the time lag? I'd say the time lag is anywhere from 5 to 25 years in the gap between what's state of art versus what's state of practice. And it depends a lot on different circumstances and scenarios. I've talked with some industry contractors who do work for investigation for nuclear facilities, and they're doing some practices that are 25 years old. And in some other cases, they're doing much more modern practices and tools. From that standpoint, what I've seen is that it's very agency dependent. If I think of the different national agencies I've worked with, and their posture, and as well as state agencies. And I think there's actually a real opportunity for leadership in advancing new technologies. And it comes from two parts. One, it comes from this is a community where things are high risk and high consequence. And as a result, one measurement or two measurements is never enough. The answer is you need multiple measurements for confirmation, for double checking even what our standard, or trying to minimize the uncertainty coming from our standard tools. So if you're using tools already, you probably want a third tool, and there's an opportunity in contractual language and in guidance to request or to help fund the development of new technologies, which can be proved over a series of years, being tested side by side with old or existing technology. So depending on how contracts are written and depending on how projects are reviewed, I've seen in other industry sectors, the ability to actually directly fund the development of new technologies, all the way through the other extreme, which is you're stifling the advancement of new technologies. So there's a wide opportunity there, I think, contractually.
Okay, thank you. And I have another question for everyone, and it's related to the computation and the computing power when it comes to new technologies. Is computing power a limiting factor in processing and making sense of the data collected, and particularly if you're combining methods?
I guess I'll go first. So when we first started developing our ERT codes, we realized there was we wrote it in parallel because we realized that, on the computers that were available then, you couldn't do 3D, for example. It was really difficult to do. Since then, most of the work that we do, even on our big problems, the computer we use is a decent sized desktop, maybe with 80 cores. This is a $15,000 computer, for example. You don't have to go to Google or something to do the data processing the type that we do. When we do really big ones and they're doing them really fast, then we have to go to our supercomputers, but that's these days is rare. So none of the methods that we use, even in the AI stuff that we're starting to do, where you're having to simulate data, we're not having to do most of that on a supercomputer. So I wouldn't say any of these methods, I'll let the others speak, are out of anyone's range in terms of computational capabilities that are required.
Yeah, as a practitioner, most of our work is done on laptops. It's only when we start getting into, in the 5 to 25 year time frame, of machine learning training data sets going through tens of thousands of different iterations, that I think our computing capacity will be lagging. But then again, that always seems to be evolving likely at a faster pace than what we could keep up with. So I think they go up and up, hand in hand, likely.
I was just going to comment and say I think we're at a transition point where the computational power now exceeds, in many cases, our cognitive understanding, or as well as our understanding of the principles that really drive the interpretation of the data. And so in talking with folks in industry doing numerical simulations of various types, their concerns aren't about computational power anymore. Their concerns are about the user understanding the physics, the driving mechanics underneath it, so that the interpretation coming out is reasonable and is true.
Yeah, one of our scientists, he has some inversions that have to run all night, but other than that, the laptops we have are doing just fine.
All right. Next, I have a question for John. Without a standard, how reproducible are results from advanced seismic techniques? Does each company have its own proprietary procedure?
I assume so. Our procedures, in a typical nuclear environment, we have to submit our procedures in advance and have them reviewed. But we've been using the same, for example, suspension logging procedure for at least 10 years, and it's been well evolved because we've been doing suspension logging for nuclear sites for, close to 30 years. So, but yeah, I think that's one of the reasons I made the point about needing to have standards, because right now I think the GeoVision procedure is the most well-used procedure for suspension logging at nuclear plants on the planet.
Thank you. All right, so the next question is for Dale. And not to put you on the spot, but would it be fair to say that by using an airborne EM survey early on in the site characterization process, that it could allow for a targeted drilling campaign, making subsurface characterization of sites more efficient, and therefore potentially saving time and money?
Great question. I do believe that that's the best way to use any geophysical method, is that you identify interesting targets within your data set that would require or necessitate additional drilling or some other geophysical technique as a follow-up. Most of the times we come in with already some site knowledge, some drilling that has already occurred, but I think if you're exploring new areas, the first thing you want to do is geophysics. Regardless of what type of geophysics, just go in with a geophysical program because of how rapid you can collect the data, how it's not intrusive, so you're not disturbing the site. So those are my thoughts.
Okay, great. And if anyone has anything to add, please just feel free to add in. I have a question for Tim. So you mentioned the Uin River. What is the state of practice and art in monitoring tritium in ground and surface water?
I mentioned, what was the first part there?
So the question that we had is, you mentioned the Uin River. Uranium.
Oh, uranium in the river. Yeah. Okay, so if we were able to see tritium in the groundwater with ERT, we would be rich. And Dale and I at least wouldn't be here because we'd be retired. Usually you can't see, there's not enough contamination in the water that you can see it. There's not enough of a fluid conductivity contrast that you can see. There are some exceptions, and most of those exceptions are at Hanford because some of the contaminant concentrations are so high. So that it's an interesting way to work. But what we can see is the water moving. So if you have concentration measurements from well bores, and you can see the water moving with the ERT or with other methods, you can put that in a groundwater model and predict, for example, what's the uranium flux to the river. And that's just how we use that data at Hanford. So it's just another source of information. You're never going to measure, in most cases, contaminant concentrations with geophysical methods, but it does help you understand the process or the structure that guides how contaminants are moving in the ground. Yeah.
Okay, so the next question, John, I'll start with you, but this is really aimed, I think, at multiple speakers here. But what are the challenges in developing consensus standards for surface wave testing and for other methods?
I think the biggest challenge right now is that in the commercial world, there's a huge, a wide gap between what I would call this very simple, for example, REMI, refraction microtremor, method of surface wave testing, which is promoted by equipment suppliers, and there's a simplified way of doing it, and then there's a more comprehensive way of doing it that involves using multiple tools and making sure that you extract all of the data out of the site. So I think that's the challenge, is bringing consensus into the community about what is the right way to do it, and when is it appropriate to be really simple, and when is it appropriate to do a more comprehensive job. And obviously, when we're, the sites we're working at that are dams and critical structures, nuclear plants, you've got to be thorough. You've got to do all of the tools. You've got to do use the whole toolbox. But sometimes that's it's just not necessary, for certain commercial purposes.
Just to add a comment to that, in reflecting on the question, it strikes me that there could be potentially separation of acquisition of the data, which could fall more into a standard, which is the hardware and implementation component. And then when the data is acquired, then there is an interpretation of that data to yield said geophysical map, or for that matter, anything else, PDA analysis for piles, all kinds of things. The first step is a hardware acquisition piece, and I think that's quite amenable to an ASTM standard. The second part is an inverse analysis interpretation process that has changed in time past, and that will continue to change, I think, and maybe even faster and faster with the computational tools. But if the acquired data is standardized, then on the second part, the way you can address the second part, as you would with any other type of interpretation process, is you might contract multiple people to take a look at the data, or multiple people to interpret it, and then to arrive at a consensus representation of the site conditions. And so I think we won't see probably a standardization of the entire thing all the way to your VS profile. You could see standardization of execution of the hardware to acquire and to deliver a baseline set of data.
I'll add a little bit to that. I think we geophysicists consider ourselves cowboys, and we like to do things our own way, and we've been taught under specific people who have done things their own way. And I kind of fight against the standardization of acquisition to some degree. If we did a standardized method, we would not have been as successful as we were at, say, the Hanford site in understanding how waste has leaked from under these underground storage tanks. Some methodologies, when it comes to engineering practice, I can understand the need for standardization because everybody has to use that data, right? So, I guess that would separate the science side of geophysics from the engineering side of geophysics.
Anyone else? Okay, so we're hitting our time limit here. I do want to add, we had one question for the NRC on do we expect SMR and microreactors to change how we do site characterization? I think we're definitely, this was probably one of the drivers for having this session today is having the opportunity to look and explore all of the different techniques that are out there for doing site characterization. And I think we've definitely learned a lot today. And so with that, I'll close with a thank you to all of our speakers and panelists today.